In this example, we're talking about input and output impedance structures for a pair of simple circuits. The input and output impedance of a simple RC network. And here's the factored pole zero form. The input impedance of the left-hand diagram is simply the sum of the two reactances, which immediately is put into normalized form with an inverted zero. Its output impedance is the R in parallel with the C. So that's product over sum, and in one line the impedance is the resistance with a single pole related to the CR time constant. The graph that goes with that for the ZI, that's the blue asymptote, it's an inverted zero with the infinite frequency value equal to R. As you come down in frequency, the inverted zero gives you a concave upwards corner at omega 1. The corresponding phase graph is 0 degrees at infinite frequency where the value is flat, and because it's a zero, it has a plus 45 per decade slope, and so it will end up at minus 90 degrees at zero frequency. That's the input impedance. The output impedance is a single pole function where the pole is the same frequency as the zero of the input impedance, but this time it's a normal pole, so the green asymptote shows the value of the output impedance, which is R, and it has a concave downwards corner at omega 1. And the phase angle that goes with it is a minus 45 per decade slope centered on the corner frequency. So that's the result for the left-hand network. For the right-hand network, only slightly more complicated. The input impedance is the sum of three elements in series, but the two resistors are just in series, so again you get a single inverted zero representing the shape. For the output impedance, now the R1 is in parallel with R2 in series with 1 over SC. So again, in one line of algebra, you get the corresponding resistance together with a pole and a zero, inverted in this case. So the graphical construction that goes with that is for the input impedance, it's an inverted zero function, so the flat value is R1 plus R2 at infinite frequency. As you come down in frequency, you encounter the inverted zero at omega 3. Phase angle, again, 0 at infinite frequency and plus 45 degrees per decade at the corner. For the output impedance, the infinite frequency value is the coefficient in front because the pole and the zero are inverted. So that is R1 parallel R2. That's the green asymptote at high frequencies. As you come down in frequency, you encounter first the inverted zero at omega 4 because that's higher frequency than the omega 3, regardless of the numbers. It has to be that way around. So after you come down around the inverted zero, you level off with the inverted pole at R1. And the relative positions are always the same, regardless of the numbers, because R1 is always bigger than R1 parallel R2, and R1 plus R2 is always bigger than R1. In the phase graph for the output impedance, since we have both a pole and a zero, there will be two asymptotes going in opposite directions, and whether or not they overlap will depend on the actual numbers. The case I've actually shown here is where there is a relatively small overlap. I've also noted on the phase asymptote what the maximum phase lag is using that little simple result that we already derived in general when you have an overlapping pole and zero. So that completes the solution of that exercise, a little workout again in drawing asymptotes related to certain analytic functions.